A simplified map of an area of moorland is shown below. The vertices represent farmhouses, great, and the arcs represent the paths between the farmhouses. The weights on the arcs show distances in kilometres. Ted wants to visit each farmhouse and then return to his starting point. In your answer book, the arcs have been sorted into increasing order. Use Kruskal's algorithm to find the minimum spanning tree. Right, well we know how this works. You just take them in order, one at a time. So CD, we'd add to our network. There it is. DE, we add to our network. AB, we add it to our network as long as it doesn't create a cycle. If it doesn't. CE, oh, CE would make a cycle. Let's reject it angrily. FG is fine. BC is fine as well. AC, oh, that would make a cycle. We reject it. EF is fine. And then from there on, well, we've connected them all. So that's kind of our stop point. We could, if we wanted to, show that we then wouldn't connect anymore. BF would create a cycle, and so on. The question then said, hence find a root. Oh, give its total weight. Sorry, so give its total weight, which, if we add them all up, the total of those ones there come to 51. It then said, using your answer, find a route visiting each farmhouse and returning to the starting point, which has length 82. So we've got this 51. We need to turn it into a route with length 82 that would work. Well, let's think. If we did this path, starting from A, if we went A, B, C, D, E, F, G, then A, B, C, D, E, F, G, like that. We then need to return home. That's our 51. How can we get back from G to A? Well, if we look at the original network, if we go from G, what would be the shortest path here? If we went back to F again, and then the 14 to B, and then the 8 to A, that would take us back by, I think, the longest route. So there we're going to do from G to F to B to A. That's the 51 for that lot, plus the 9 to F, plus the 14 to B, plus the 8 to A. And that's our route of 82. And that's answered all that we needed for that. Part 2. Give the weight of the minimum spanning tree for the 6 vertices A, B, C, E, F, G, and hence find a route visiting each of the 7 farmhouses once and returning to the starting point. Right. So actually what we changed here, we've missed out vertex D. If vertex D wasn't there, I think it's quite easy to see actually. If vertex D wasn't there, the minimum spanning tree would just involve doing that. We've got this pattern already, but we just, instead of C, D, E, we just go direct from C to E, and that would still give us the minimum spanning tree. So our new spanning tree would be, if we did that in part 2, it would be A, B, C, E, F, G. So that would be the 51 that we had before, but we've removed the 5 and the 7, and we've added in the 8 to replace them, which equals 47 as our length for that. So what would our route look like if we did that now? If we did visiting each of them once and returning to the starting point, we're now going to do that. So A, B, C, E, F, G, and we haven't been to D. So we're going to go back from G to D and then to A. So that's 18 and 16. So that's our 47 plus 18 plus 16 gives us 81 as our new route. So we kind of started with our minimum spanning tree and turned it into a route, which is a little bit unusual because we normally do this kind of stuff using the nearest neighbour algorithm, don't we? So now we're on to part 3, show that the nearest neighbour algorithm, nearest neighbour method, fails to produce a cycle through every vertex when started from A, but then succeeds when starting from B. So we need our diagram. I think we might just take a copy of our diagram here. There it is. So let's work our way through this. If we start at A, we go from A. The nearest one would be B. There. The nearest one to B would be C. The nearest thing to C would take us to D, and D would take us to E. When we're at E, the nearest thing to that would be F. The nearest one to F would be G. But now we've got a problem, haven't we? Because we've gone A, B, C, D, E, F, G, and we're supposed to get back to A. And in the nearest neighbour algorithm, we're supposed to do that directly. And there is no direct route back to A, so we stall at that point. No direct route to return to A. We're stuck. We give up. Then it says start at B. If we start at B, we would go to A first, a distance of 8. From A, we'd go to the nearest one to that, which is 11, taking us to C. The nearest one to C is D, at a distance of 5. The nearest one to D that we haven't yet been to is E, 7. From E, our nearest one would be F, a distance of 12. The nearest one that we haven't yet been to from F is G, a distance of 9. I think we've been to all of them now, haven't we? And so we need to go back, but this time we can go back directly. The direct route back to B is a length 24, and that gives us a total of 76. And was that what it asked us to do? It then said, adapt this, when starting from A, but then it succeeds when starting from B, adapt this cycle to find the complete cycle less than 70 and find the shortest length. Well, what have we just done there with that cycle? We've gone B to A to C, D, E, F, G, and back to A. That was the cycle that we started with. How can we adapt it? Well, what are the issues in this cycle? It's this little bit here that's the problem, isn't it? Doing that bit there. And we noticed that if we'd actually, from E, if we'd gone to G, and then to F, and then to B, if we changed our cycle and done that, at that point, then that would have been more efficient. That would have saved us a little bit. So the adapted cycle is the start bit is fine. B, A, C, D, E, but then we're going to change this last bit, and instead we're going to go to G, which is 15. We're going to do the 9 that take us up to F, and then we're going to do 14 to take us to B, and that comes 1 under 70. We've saved ourselves 7 by doing that route, and that would be our answer. Great. Stop the video.